Maybe at least dual. It was a $400. Oh, okay. It's not so hard letting go.
Yeah, so this is $400 computer that I bought. That's like 2,000. Yeah, it's 2016. So.
Not like half that. You have perfect.
Yeah. It's just
deleting this.
Although what is kind of like a fun.
If it's not due to like.
I might leave it. I'll do it in my brief. Put it on my resume.
Also, there's the barbecue.
Like, is that actually, like, are you gonna send that out?
So it's gonna be on Monday, but we haven't decided the parts. I don't wanna go to Sloan this late because it's gonna be hellish there. But if there's like a smaller part somewhere in the North Denver area, like somewhere on the outside of town.
Yeah.
Let's do a blue screen. It's actually brilliant. Just go to the bar. You're just going to.
So the number of online students is slowly increasing. So hopefully it will not happen that we're gonna have more students online than physical. That's
No more snow days.
yeah, that's true.
All those are on to.
So if a programming language has any special cases, it's less orthogonal, right? So it's all the others hold like consistent use of features, few exception rules, clean design, clear rules. So that's all characteristics of orthogonal language. It's kind of more difficult concept to grasp, so that's why I'm giving you some examples. Another example that talks about orthogonal design. I think streams is an example of a good orthogonal design or not. Why?
So many exceptions.
Very good.
Yeah.
Actor. So,
Yeah, okay. There.
yes, right, because you can read and write from any streams the same way, right? That's why I would say it's a good orthogonal design. if you would be able only to do for a few streams, right? And then for other streams, you have to do it in a different way, so that's non-orthogonal. You're grasping the concept better now?
Yeah.
Last time we briefly discussed the phases of the compilation process. So what do you think that is? Works so well, you use that. So 70%, that's good. It's the syntax analyzer. How about this one? Do you remember which phase is that one? Which part of the compiler is responsible for that? That's the lexicon analyzer. It's part of the compiler that you will implement. Did you bring your card?
You already got it.
Oh, already got it. You were fast. You just.
Well, I saw it coming up, so that was the first thing I grabbed.
Okay, so this is actually a semantic error. Because it requires an extra step, like the syntax analyzer will be able to create a structure of your code that says, oh, that's starting a, let's say a function definition, right? And it will make sure that a function is defined syntactically as having like a header, right, and a body, which is the actual code for the function, and the mapping of whatever you're returning to the actual value that you specify in the header. That requires a semantic, because you need to match the types, right? So that requires something that only later phases of the compiler, will be able to do that. Okay. But we're going to see that, discuss this in more depth later. Okay. All right. Cool. And today we're going to start the compilation process, and to do that, we need to understand a little bit about how programming languages are formally defined. I'm going to kind of do a review of some of the concepts that were probably introduced in theory of computation 3240. If you haven't taken 3240, that's fine. Although it's a prerequisite for this course, but I'm going to do kind of a, hopefully you'll be able to get a good grasp of the fundamentals that we need for programming language. Okay, so if you want to follow along, will be lecture slides number 4. So in order to define, formally define a grammar for a programming language, you need to introduce some basic concepts, starting with an alphabet, right? So the alphabet is the set of symbols that you're going to use to write your program, right? So it consists of all the symbols, including the alphabetical symbols, the numerical symbols, and other symbols like arithmetic symbols, assignment, special symbols. So all the characters that you're going to use to represent words, right? So you're going to use the alphabet to create a sequence of symbols. So you're going to get the symbols of the alphabet and combine them and create sequence of symbols. Those sequence of symbols, we're going to say that they are words, right? This is a very breaking down, right, in very specifics of how we formally define a code, like a program that you're going to write in a specific programming language. So you have, for example, for, right? So you want to write a for loop. So for is a word made of the symbols F-O-R. Okay? So if W is a word, we're going to use this notation with the pipes to denote the length of the word. And we're going also to define a special symbol in our alphabets. Well, this is actually a symbol that you're going to denote using the epsilon, and this is going to be important in when we define rules to generate words in our programming language. There are recursive by definition. So we use epsilon when we want to end the recursion. Okay? So keep in mind that epsilon, there's no visual representation for the epsilon other than we're going to use, when we write the formal definition, we're going to use this symbol. It's a Greek letter for epsilon. Okay, so this is fundamental. Here's an example. And before we, and this is to simplify the examples, we're not going to start showing examples of programming some programming language. We're going to use very simple grammars, just so we can practice easily. So think about that. This is a very small alphabet, right? Just two symbols, okay? A and B. And you can think that A, just the symbol A, is just a sequence that uses just one symbol, and that's considered a word that we can create from this alphabet, right? And the length of this word is 1. It's pretty obvious. But you can create other words, like AB is another word, size 2, and this is BBB, 4B, so another word, size 4. So, of course, if you have a finite set of symbols in your alphabet, you can create as infinite number of words, right? You just combine those symbols. We're going to say that a formal language is a set of words from an alphabet. So if you get an alphabet, you have potentially an infinite number of words that you can generate. A subset of those words is going to be a formal language. Okay, so you can have a formal language that is a finite set, or you can also have a formal language that, by definition, is also infinite, right? Think about all the programs, right, that you can generate from some alphabet. Think about how many names you can give for identifiers, right? So you can combine letters of the alphabet. If there's no restriction on the size, in theory, this is an infinite language, right? So consider this is an alphabet AB. Just these 3 words put in a set, this defines a formal language from that alphabet. A very simple formal language that only contains 3 words. So now let's formally define what is a grammar. Okay. So a grammar is defined by these 4 components. First, you will define a set of variables. Okay? So variables are going to be intermediate symbols before you actually generate a word from your grammar. So we're going to use these temporary symbols called variables. And then you're going to have T as a finite set of terminal symbols. Those terminal symbols are symbols from your alphabet. And then you have a set of production rules. Production rules are, they use the variables and they use the terminal symbols, and they define how to go from one state to another. Okay? As the name suggests, they are used to produce a combination of variables and terminals, and you're going to keep doing that until you generate a word that only consists of symbols, terminal symbols. And you have to start at some point. So there is one variable that is called the start variable. That's where you begin your applying the production rules in order to generate words using this grammar. Okay, so this concept of defining grammar for a programming language, it allows us to use the grammar to produce words that are part of our language, right? So you can think of grammars as a mechanism to generate words that will be in our programming language. You guys in theory study automata theory, right? Automatas. So the automatas, basically they recognize symbols, whether the symbols are in a language or not, right? So if I give you a symbol, you go through all the transitions, and you, at the end, if you reach a final state, it means you recognize the symbol. Here, it's different. You will apply the production rules starting at the start symbol, and your goal is to prove that you can generate the word that is part of the language. Here's an example of a grammar. Okay, so this grammar has only two variables, s and d. S is the start variable. Okay, so you have to start using s, and the terminals are only the digits. Okay, and the production rules are usually described using arrows. It's a set of productions. Okay? And what it's saying is that from the variable s, which is the start variable, you can go to d. But there's also a possibility that from s, you can go to ds. And from d, you can go to each of these terminal symbols. Once you move to a terminal symbol, you can't go any further, right? It's terminal. The variable allows you to continue using, by doing these constant substitutions, you can eventually reach out you can substitute all variables, and you end up with only terminal symbols. Those terminal symbols is the word that you generated, okay? The generated language is you given a grammar. The generated language from that grammar, denoted by LG, is the set of all words that can be derived from the start symbol using the productions in G. Okay, so if you consider our example, our grammar from the previous example, the language generated by that grammar is infinite, right? Because, for example, can you generate 0? Right? So you can easily generate 0 because you start at S, right? From S, you can go D, right? That's smart to use this production, right? Because I need only to generate 0. And from D, I can generate any of the digits, right? So 0 or 1 until 9. So I can go from D to 0. So I was able to generate 0. So 0 is part of the language generated by the grammar. Now, of course, using the same reasoning, I can generate any single digits. How about to generate 2 digits? Let's say I want to generate 0, 0. So which production should I apply? DS. The DS, right? So I apply DS. I don't have a good. Not used to use the whiteboard anymore. So where's the virtual white? So from S, I can do DS, right? Still not good. Well, from this D here, perhaps I can do S to D, right? Or I can do D right to 0. So I'll have 0 S, right? And now I can do S to D, right? So 0, D. And then now I can turn that D into a 0. So 0. Okay? Well, that grammar allowed us to generate zeros on the left side. How would you change that grammar to avoid generating numbers with 0 on the left? So for example, I want 0. Okay, so that's just the 0 as the first single digit. That's okay. What I don't want is 0, 0. Okay. I can have 1, 10, right? But I don't want 0 on the left side if the number has more than one digit. Why don't you try to change that grammar in order to avoid generating zeros on the left side as the most significant digit? Okay, I want to avoid 0, 0, 0, 1, 0, 2, 0, 3, or 0, 100. I don't want 0 on the left side. Why don't you guys work? Maybe with COVID, I can't say work together, right? I guess you can. All right, so you know what to do? So try to figure that out. Use some time to work on that.
Make D want to go from 1 to 9 and then make another. Yeah.
You said change the reductions, right?
So we can only change.
It is changing a reduction.
Look, isn't that adding a variable too? You have to add a new.
Oh, S to D and then S to S.
Well, you could,
Just
S goes to D.
and then make another rule that you can only add 0 from a different digit.
On
Yeah, we
next.
just add another.
right, because S has to go, this current setup, it has to go to D, the front end at some point.
So move 0 and then make a production rule special for 0 if you want 0.
Yeah,
that
S goes to
that
E.
goes from 1 to 9
Like
to
D and
0.
Yeah, it's like S goes to.
S goes to D.
S goes to E, S.
Well, you don't want E at the beginning, because then you could still get 0 on
Well,
the
that's
left.
oh, sorry, I was thinking E was your.
What about S goes to 0?
So say D.
S goes to D, S goes to E, S goes to 0.
S go to. Have S go to 0. E, S.
So it'd be like 0.
Yeah.
S goes to, so it could go to D.
Right.
It's
Right.
still-
It
it's
goes
still
to
D.
E could go to,
S goes to D.
or sorry,
We have to do it.
or D,
Stuff.
or ES.
Yeah, I think I like your
S
approach.
goes to 0.
And then S can go to.
S could go to DE,
Because then
because you still want,
here when
you don't want the E to be on the far left.
Right.
And then you could have D go through 1 through 9 and E
So
could go to 0.
1 through 9, that's your.
S goes to 0.
So S.
Or you could still have that DS.
Or S can go to. Like 0.
So S goes to 0.
No pride.
To 0. Absolutely 0.
Yeah.
You could.
Well, I'm working on it.
1 to 9 or 2.
Is it?
Let's see what I can do.
You just make it so there.
We're trying to program.
So it'll be a terminal of 0. That'd be my approach.
It's like the first position, basically.
So then E can just go to 1.
That.
1 is constant.
Rolls as much as we want.
She sneezed.
Just make 1 through 9 0 like a special case where it's only introduced in the start variable.
Okay.
To D.
We do.
Oh,
So.
so then it's just 0 through 9.
Really good.
Well, all we're doing is we're making
Found one?
No,
through 9 and
no,
E.
I saw this.
So like D could go
Oh,
through, go to 1 through 9, or it could go to E. And E has to go to specific terminals followed by a 0. So then you only end up with zeros on the right. Like, you could do E going to 1 0, or 2 0,
Really, really 0.
all the way through 9 0. But you'll only end up with
Where
zeros
this
on the
guy?
right.
I wrote it down.
No. Good. What are you doing?
Just thinking about it.
You need to have one of these tests.
Why is it
Seems lonely over there, man.
So the solution
Usually isn't.
Well, there's not just one solution, so if you do it differently, I want to hear it. But this is one possible solution. You have S going to D, okay? And this D here can go from 0 to 9, so it's that normal D, right, from 0 to 9. And then there's another possibility, S going to D prime, S prime. Okay, so the D prime, so we want to make sure that the most significant digit, if I'm using more than one digit, that it can only go from 1 to 9. So D prime goes from 1 to 9. And then, of course, I want to generate more digits, so that's the S prime. S prime can go to D, that's a normal D, S prime, or D. So that allows us to produce many Ds as we want, and those Ds are normal. But the most significant digit is a D prime. That guarantees that D prime only goes from 1 to 9. Okay? Make sense? Okay, so let's use it to generate, for example, we want to generate, let's say, 1 0 0 1. Okay, so we do S, we go to D prime, S prime, right? This D prime can only go from 1 to 9, so I can generate this one here. And then S prime, I can use it to pump, right? Generate many DS. So this is, don't you guys see that this type of production is recursive? Because you have S prime on the left side and you have S prime on the right side. So these recursive productions, they're of course useful when you want to do repetition, right? So I can do, I'm gonna do DS prime one time, another DS prime, right? And another DS. Now I want to turn that S prime into D, right? Because I only need to generate 3 more digits. That looks like a base case of the recursion, right? So I'm just going to turn that S prime into D. Otherwise, I'll never end, right? And now the D's, I can just turn them into the digits that I want, right? Okay. Okay, so the most simple grammars, so there are depending, we're going to classify the grammars, the form of grammars, depending on how we're going to allow the production rules to be. Okay, so if we put a lot of restrictions on the way we write those production rules, we kind of limit what type of programming language we can build using those grammars. Okay? The most restrictive one is called the regular grammars. Okay, so the regular grammars are used for regular languages. They are more restrictive. Okay? They have, and there are even more restrictive grammars than the regular grammars. So this one is called left linear. So the left linear grammars, they will only allow these type of productions. Okay, so you can have variables. So first of all, on the left side of the production. So remember, production, you're gonna have a variable, a combination of variables and terminals, okay, and an arrow. And then you're gonna have on the right side of the production a combination of variables and terminals, right? On the left side of the production for those type of grammars, the left linear grammars, on the left side, you can only have one variable. So you cannot have a combination of variables and words, okay? You can only have a variable, okay? Single variable. On the right side of the production, so here, you can only have a single variable. Okay? On the right side, you can have variables and words. But if you have a variable, you can only have one variable, and it has to be, and if it appears with a word, it has to be on the left side of the word. Okay? So that's why it's left linear. Okay? You see the B is appearing on the left side of the word. Word is a combination of terminal symbols. Or you can have just terminal symbols. Okay? So this is how restrictive those grammars are, left linear grammars. So if you have, basically, it's saying that, okay, A and B they can be the same variable, right? You can have recursion in left linear grammars, right? But if I have recursion, the recursion is on the left side. It's not on the right side, okay? So let's see some examples. This grammar here is left linear, okay? So let's look at each production. For example, this first production here. How many symbols we have, how many variables we have on the left side? Only one variable. That's good, right? Now let's look at on the right side. On the right side, I have a variable and I have a word. AA is a word, right? And I only have, right, one variable, and this variable is on the left side of the word. So it passes on the criterion, right? How about this one? S going to ABB, same thing, right? You have a word and the variable is on the left side of the word. How about this one? This is a recursive production, right? But it's okay, you have one variable on the left side and you have only one variable on the right side, and this variable appear on the left side of the word. It's also okay, right? This one is also okay. You have a variable going to a variable in a word, and the variable on the right side is on the left side of the word. And you have epsilon. Epsilon is fine. So it's a left linear grammar. Okay? What kind of words can we generate with that grammar? What do you think? I'm going to give you some words here, and I'm going to ask you to check if I can generate those words. For example, can I generate AA? Can I generate BB?
Yes.
Can I generate AAA? Can I generate VAA? Yeah. No.
No,
Yeah, you gotta start with the start terminal, you're gonna take two A's.
So let's check. The first one, S. I want to generate AA, so should I use the first production or the second? First, right? And now what? A goes to F. So the first time you're seeing an epsilon production, maybe. So A go to epsilon means get rid of A, okay? So if I using this, I'm applying the epsilon production, okay? So yes, I was able to do that. BB is also fine, right? I can do A, BB, and then get rid of A by applying epsilon. How about this one? So I have to do what? First one, right? AA. And then A I can do as many times as I want, right? Generating A's and B's, right? And I just want to generate one A, so I'm gonna do AA. So A going to AA, right? And now I can get rid of that A, applying epsilon. And here I just need to, can I do that? Well, the first one, so I have to do AAA, right? So S going to AAA. But now this A, I want to turn that into a B. So I'm going to do AB, right? And then I get rid of A, BAA. I was able to generate that. So if you were to describe the language of that grammar, how would you describe it?
Let's say it's any combination of A's and B's that ends with two A's or two B's.
That's a good way to, very succinct way to put it, right? Any combinations of A's and B's, but you need to finish or end with two A's and two B's. Okay. Good. Excellent, actually. So now let's look at right linear grammar. Okay, now that you mastered left linear grammar, how about right linear grammar? So as expected, the right linear grammar has the same restrictions. The only difference is that that symbol on the right side, that verb on the right side, is on the right side of the word. That's the only difference. So that's a right linear grammar. Here's a right linear grammar. Okay, let's check if it's right linear. Well, first of all of the productions, they have, on the left side, they have a single variable. This one, I guess these three productions, they have an S, and these two productions start with an A, so they're good. And on the right side of the productions, if there's a variable, the variable is always single variable, is on the right side of the words. That matches all the cases. Okay? So it's right linear. Good. Don't you have the impression that you've seen that grammar before? Or not the grammar, but the language generated by that grammar? Aren't you having like a deja vu? Different grammar,
It's the same.
but it generates the same language, right? Don't you agree? But it's right linear. So first, you can use these productions here to generate as many A's and B's as you want. When you're tired, you decide to go to A, and A has to go to either AA or BB, ending the word in an AA or a BB. So it's the same thing, right? So it's a different grammar, but generating the same language. So, going to programming language, you can say that you can define the same programming language using different grammars, right? Designed differently, but it might be used to check the syntax for the same programming language. as this is just to show that these two grammars, you can always turn a left linear grammar into a right linear grammar and vice versa. So they are equivalent. And this, we're not gonna, if this was a theory computation course, you would prove that they were equivalent, okay? But this is not theory, so yeah, you have to prove that.
Say that again.
But we can do some reasoning and try to figure it out. Like, for example, this is another, this is a right linear grammar, right? So I want you to find a left linear grammar that is equivalent to this one. So try to see if you can find it. Rewrite that grammar as a right linear grammar. Okay?
Has to start. Start here. Always. It starts with A.
It starts with A because A can also be. So it starts with A. Yeah. Because A can go to B. Right.
It's just start. At least one A.
Right. Yeah.
Everything we want first.
Let's make sure to do that answer.
We'll go best.
So it has to start with A. Right. It has to. We can't have it like a mini version.
Yeah. Let's make sure that all states that's the issue.
So it has to be.
Help us out.
B, you have to. A. So it has to be.
Yes. Or alternate.
It has to start with A.
Right. It's confusing.
It's not followed by B. Has to start with
Yeah.
little b, big.
Because if you want to get another A,
It has to have a B first.
right. So you need a B to get an A. That's the second rule.
Yeah.
So it can either be-
You
No, it's interchange, it's
Any
A,
number of
B,
B's.
right?
No, it's
Oh, wait.
for the A, B, A, B, A.
Yeah, because S and then A, B, B.
Wait, right. Right,
And
then
then
B
B.
goes to A, followed by an A.
But it goes here. It goes to.
Starts with an A, goes to
And then
B, and then goes up.
You can have multiple B's.
Yeah, but the key thing is
starts with A, B, B, starts with A.
Right.
Yeah, but
So,
like,
we have to have-
It's not
Right.
so I think it's start.
Yeah, so like S goes to A, right? But that's the only
A, B, so it has to start with an A.
Yeah.
And then we can only have one B. So, but we can have
Yeah, this is the same over, it's what we heard it say up there.
and you have to start in.
Wait, so
Could just be number two.
So, but for every B that we have is followed by
Yes.
so we have any number of A's, if there's a B,
Cannot have standalone.
you can't have B's together.
we have.
Any number of A's, any number of B's, as long as they're not together.
We're just in the grammar.
Oh, yeah, we have to write. On the left. The last one? B equals A.
So it would just be A goes to A.
I mean, our homework is
Oh, so you can go ahead.
Yeah.
I was just doing big A, little B. Okay.
Or you could do something similar to this one too.
No, I think yours makes a little more sense.
Galaxy?
Yeah.
So.
So, sometimes it's easier to try to describe the language first and then try to figure out how to implement the grammar in that format. How would you describe the language first? Right.
So it always starts and ends with an A, and you'll never have the same terminals touching.
Same terminals, what do you mean touch?
So like A will never be next to an A, and the B will never be next to a B.
Can maybe, let's try to do more, like for example, there is some repetition on the B and A's, right? Because here we go from B, and then B goes back to A, right? Letitia, want to try?
A collection of words of odd length involving alternating A's and B's, always beginning and ending with A's.
Always begin with an A, right? And after that, you're gonna have alternating BAs, right? But the order is important, right? You can't have ABs, it has to be BA, right? So you start with an A, right? And you can have as many BAs as you want, including non, right? Right? Okay? Okay? So it's so now that we have an understanding of the language, the words we're expecting to see on that language, you guys want to try to put that in left linear format? Yeah.
So I tried something really simple, and so far I haven't found a way that it's wrong, but it might be too easy.
Go ahead.
So all I did was move the lowercase terminals to the other side in every case. So instead of S going to little a, big A, it's going to big A followed by little a.
So from S, you go to what? More.
I go to capital A, lowercase a. And then from capital A, it goes to capital B or lowercase b, followed by lowercase b, not other. Or the empty string.
Or the empty string.
And then capital B goes to capital A, lowercase a.
capital A, or
Just and followed by a lowercase a.
lowercase
A.
a, right?
Or just lowercase a.
Okay, so, okay, A, and then you can do many EAs, right? And you can go to epsilon. Yeah. That works, yeah. And it's left linear, right? I did S going to S A B or A. Right? Because this will allow me to do many ABs, right?
And then finally end with an A.
And then ends with a. Anything different you guys did?
Doesn't there's a AAB? Wouldn't you end with AAB if you want to do one of the first, one of the second?
Maybe it's the ABS.
So AB, a sequence of ABs, right?
What's that?
I can do a sequence of ABs, right?
Yeah, and then so just do one SAB.
Oh, and then it would,
Yeah.
and then the A would be at the beginning, not at the end.
Be on the right side.
You could write a.
What I did is I just flipped everything. So like if it was a lowercase b, I made it an uppercase A. And it only failed on the, I only had to change the starting.
But you can also add a
Lowercase a to make it.
Because it tends to start with an A, and you can have as many ABs as you want, right?
So it's not mine, it's not.
No, the language, right? For that grammar. You start with an A, and then you can have as many ABs as you want, right? Or not, right? And that grammar allows you, if you keep doing S going to SAB, you can produce ABs as many as you want. When you're done, you go from S to A, right?
You just need to change A and B.
Here?
Yeah. Because you can't have B on the very right, can you?
Yes, you can, because when you go from B, A, and then A, you go to B. Oh, yeah, you're right, because you have to go from A to epsilon. So the language that we described wasn't right. Because you can produce as many ABs, but you have to finish.
So I think you can start.
Okay, so you just need to switch B and A.
Yeah, that's what I thought, yeah.
I was overcomplicating. All right. Okay, sounds good.
Right, with that language, I thought you could do, you could end with an A or B, I thought. It has to end with an A, because the language that you just put.
It has to end with an A, right? So it's actually BAs, right? So start with an A, and then you produce BA, as many BAs as you want, not as many ABs as you want. And I said initially ABs. That's why I was confused. So it's not ABs at the end, it's BAs at the end, okay?
Okay.
Just to clarify that, I said AB in the beginning. Okay, so but both work. I guess this one here, I think this is a mistake, right? Because it has to be BA, right?
But your S goes to dig in the left. So you always have the land right. I think it's right.
So, oh, because, oh no, this is the left one, right?
Yeah, they're a little backwards. Yeah, that's a lot.
Okay.
So you really got your right.
So that's another one. Have S going to AA, and then A producing as many B's. But it has to start. It has to start with an A. So this one looks different, right? It's not starting with an A.
You'll always start with an A because of the second rule.
Yeah. Because S goes to, oh, but you, oh, because you can go to epsilon. Okay, so moving forward, you can, now we can formally define a regular grammar. So a regular grammar is a grammar that is either, it has both, it accepts both of the restriction of the left linear and the right linear, okay? So a left or right linear grammar will fit in the definition. So it will accept both productions for the left linear and the right. Okay, so let's do an exercise now. There's an activity. That's activity 1. I have a copy for you. Basically, you need to classify these grammars as left or right linear. And then you need to show if the words can be generated by the productions. By the grammar, using the grammar's production.
No, I said.
Yeah.
Okay, so.
Right.
Man, appreciate that. That's trickle down economics at work right there.
That's write it down. You can print it.
You can just use the word.
Start maybe that's why that's it. But it's really cool.
Oh, you
But they pass it downstairs. Starting grade. Just add word.
But you can't make an extra.
Yes.
Yeah, you can't make an extra. I thought you meant.
Can't make an explanation because you still have a.
I thought you were talking.
Are they filled out already?
That's what you got first there, but I'm also
Alright, so I guess like obviously that's really like what did you something like reading yes.
Really good up there to get up to.
That is a letter. Yes, that is correct. Oh. Oh, yeah.
Let's go.
Yeah, I didn't see that. So yes. And then it's right. But no, for the second one.
I got this. Why you got this?
Because you see this board,
Okay.
so S is like a X plus S. X.
So it's literally one plus three. S goes to S.
Yes.
Then why there's no way to get.
So we start out at this.
There's no way to get
If Y is after S, it's yes.
There's no way to get X.
No.
Okay.
Yeah, I see.
So yeah. Because it has to end. So this, yes.
First one is yes. This one is yes. Goes down. Second one is yes. Second one is
Year and a half, yeah.
You guys have the same issue.
It's pretty gnarly.
Okay, that's true.
But mine's
I
like
give myself too
draw.
much credit. Also.
Okay, do you guys get the same pattern?
Yes or no, yes, or no.
I did it during class.
Twice.
I was doing it.
So take one.
No. So S produces S or S.
Okay.
Just produce Y. It's like if there is a or Y, then yes, that's it.
Really great.
So number two, we were hybrid. I was like, we're never.
How off is like some stupid weird.
Thank you. Yeah, that's right.
They go by metrics.
Hold on, so this one was
Like,
like.
like 10.
This two.
There's way more.
But also like.
Oh, we got
Is it longer too? Or is that?
It's very.
Oh,
It's like a fractal size. It's like 2 sheets of one size, side by side.
Really?
Make up the next sheet.
Oh.
Put 2 side by side, turn vertical, that's the next biggest size.
Or I keep
Forgetting that's like 2 minutes.
Yeah, it's literally like-
Like a newspaper size.
That's a lot.
But it's not in order. It's A, A, B.
Some scissors.
A, B, A, B, A.
A, B.
Yeah, I know that you can pick, but like.
Oh, I'm still on my first one.
Yeah.
You want third?
Yeah, the first one is yes, yeah.
Yeah, why?
It's going A, A, B. How that?
Well, on that, I know, it's, whatever you take us first, I think.
August 8th, no.
So yes.
Ah, it's just.
It goes from left to get A.
Get the down.
This one is gives us 2, gives us 3, is 3. Oh.
Did we just looking first?
It's 2 AB or.
The first one.
That's 3.
I'm not even
Not
gonna,
even
I'm waiting till we get out of the class to have my meltdown.
Like, it's like a first.
No, it's just
Okay.
me.
Like, every exam had your grammars on it.
Yeah.
Thank you.
You should go PPL then theory.
Okay, guys, start with your first one.
Same pattern.
Is it a yes or no?
No.
Yes.
First one is yes.
Yes.
Oh, before that, is it left or right linear? Right linear, right? And to produce X, you just need to go from S to X. How about Y?
No.
No. Right? I couldn't figure it out. When you say no, where you can't generate the word, you always think like, well, I couldn't generate because I'm not smart enough, or actually it's impossible, right? You never know, right?
Same no.
But if we all said no, I think we can maybe collectively say that we're right. Or wrong.
All wrong.
How about X, Y?
No.
Oh, I couldn't. And this one? Yes, right? So from S, go to, I guess we need to go X, Y, S, and then again, right? And then we are tired, and then just put S going to X. Okay, how about the second one here? Is it left or right?
Left.
Left, right? Left, linear. Can we generate AAB?
Yes.
Yes, right? So the first I have to do S1. Right? S1, you don't have any options, so you have to do S2AD. And now we need to turn that S2 into an A. And the way to go is to turn S2 into S3, right? How about A?
No.
No, right? Because from S1, I can only go to S2AB, and AB is more than AE, right? How about this one? No, right? This grammar produces words that end in AB, right? So because this word is not ending in AB, it's impossible. This one ends in AB. Let's try. S1 goes to S2AB. I guess we need another one. And when you're tired, you go S2 to S3. And then S3 to A. So A, AB, AD. Okay?
Sorry, why the third one is no?
This one?
No, the AB, A.
Oh, from here I turn S2, this S2 here, into S2AB again.
I'm sorry, I'm talking about the third one.
The one above
The
it.
one above it.
No.
Oh, why this one is no? Because it doesn't end in AB. All of the words of this grammar, from this grammar, they need to end in AB because S1 has to go to S2AB. Okay? Okay. How about we do some Scala now?
Yay.
So let's look at arrays in Scala. Arrays are the collections of the same type. We have static or dynamic arrays. Let's begin with static arrays. one thing that we already saw, and I believe most of us didn't like about Scala, is the fact that Scala uses parentheses for indexes. That's ugly. I don't like that. Other than that, so here, because this is talking about, we saw that when we were indexing a string in a previous example, but now that we're talking about arrays, this is obvious. Make sure you remember that if you index an array, it's kind of odd from most programming languages use the brackets, and there is a reason for, the reason is readability. When you see the name of an array, and you try to index that array using parentheses, it reads as a function call. So it reads really bad. It was a bad design decision. Static arrays, here's an example. Perhaps you want to run this code to see you're declaring an array using val. Remember, val use when you want to specify variables, not constants. Var is for constants, var is for variables, vals for constants. So it's this array here. I don't expect to reassign, so that's why I'm using val. This is actually improves a little bit of the reliability of the code generator by using var and val. Because if you know that you're not expecting to make changes in that reference variable, right? You can still modify the array by indexing the elements, but you're not expecting to use that same variable, that same reference variable to another array. So you're not going to reassign the reference. So it's a protective mechanism to define that using val. Because if you, for some reason, you change the reference of that, change that array to refer to another array or something else, the compiler will check that, okay? Because you said it was val, how come you're reassigning that variable, right? So it's a protective mechanism, improves reliability of your code. The new here is optional. And the typing here is also optional. Explicitly typing, you don't have to do that. What else? How you iterate over an array. You can iterate using the indices like I, so you're going from 0 to n. Then you subscribe the array, an array index I. Or if you don't care about the indices, you can just iterate over its elements using this syntax here. And there's an option to create a static array just by initializing its elements. So vals here, we're just going to enumerate its elements. This is how you specify that in Scala. So why don't you guys run example 21 and 22, create a project, just so you start to become familiarized with Scala. Run example 21 and 22. So homework 2 was assigned, and it's gonna be very similar to activity 1 we did in class.
You're like, they actually make that. I mean, they're just going to. They have those. They have those. Yeah, ground beef. I think the ones that are free, you know. I can't tell. Because they know. I think they're shaping. You know, they probably get them in bulk, right? Because I know I buy them very shaped. Zero, like slider style. But I also know.
Size 3.
I just created on my student. That looks like
Jesus Christ.
ancestors.
Okay. Dynamic arrays. So depending on which package you use, you can use dynamic arrays that are mutable or immutable. So you have the choice. Most of the times we want to be able to change, right, the values. So we use the mutable array buffer. So again, if you from CS2, right, a dynamic array allows you to increase the size of your array dynamically, but it's still an array, so you still get the advantage of fast indexing, but it's not, it's like a compromise between a list and a dynamic list or a static array. So if you want to compromise between these two, dynamic array is the way to go. Let's see what we have here, array buffer. In this example, you guys can try example 23, allows you to enter as many elements as you want. It's interesting here that it allows you to use plus equal to append, right? To append the array. I think that's, what do you guys think? It reads well, I believe, to append an array using plus equal.
I like it better than
Calling a function or a method. Yeah,
it looks better.
I agree. What do you guys think?
Instead of using like dot append.
Instead of calling append or any function or method, you just do plus equal, right? I like that. So in programming language here, we try to look at a programming language with critical eyes, right?
So I assume you could remove
Like, the rule.
You're not wrong.
Yeah, so internally, it will adjust the size, so you don't have to worry about that.
You could say like minus equals.
Did you say
Or-
not C, tell us?
Minus
Well,
equals
no, never mind this guy.
to remove.
To remove.
I don't know, that's a good question. Maybe do some research, try to figure it out. Okay,
Or just depends. Yeah.
arrays transformations. So we're starting to see some constructs that are more interesting, and that comes kind of motivated by the fact that Scala supports functional programming, and all of these for each function, for statement looking like they're actually functions. So let's start seeing these constructs. For example, the for loop construct with paired with yield allows you to do basic using a generator and similar to what we like to call list comprehension, kind of what we're doing here. We want to double all the elements of the source array, right? So we use this for syntax. So for element in source, I want to yield doubling the element for by EL. And the result of that is going to be a new array that I'm going to save using this double reference. This one here is doing also a for, but I have a test, right? I test whether the number is even or not. So these transformations, they read well, in my opinion, they have a lot of they read well, and they have you're able to express what you want to do in a few statements, right? So they're very powerful. If you guys want to try this, example 24, usually copy and paste and test this code. So far, the examples I've been using a for loop just to print the elements of the array, but you can also use a make string, mk string method, defined for collections that will give you a string representation of your collection. It's parameterized, so you can separate the elements. You can specify how you're going to separate the elements. Okay, so this is another transformation using sorted. You can easily sort array.
They have to pass the.
The sorting is not in place, right? It returns a new collection with the elements sorted. Then the next example, you have a multidimensional array. So basically, you define the array as of type array. And then you specify the number of rows, so that's for the first dimension, right? At each iteration here, you need to instantiate the inner arrays for the columns. And then you look at the syntax for indexing the 2D array. You put each one on its own parentheses. I could have combined just one parenthesis, right?
Yeah, maybe like comma separated would have been nice.
Yeah, like NumPy, right?
Yeah.
You just put brackets and you have many dimensions. You don't repeat the brackets, right? You just put the brackets inside. Sorry, you don't repeat. Yeah, don't repeat the brackets. You put the comma inside the brackets. Okay, to conclude, associative arrays, also called maps or dictionaries, can be mutable or immutable, depending whether changes in the map are allowed or not. Well, if you define your map as immutable, like this one, when you instantiate, you have to specify the elements, all the associations, right? Okay, so this example is it says it's immutable, right? So let's check that. Let's try to modify or add a new association. To add associations, I guess you just do, again, they're using the parentheses for the indexing. So this is creating a new association, just a sign. I'm curious I want to see the arrow. We try to create a new association in an immutable associative array. Run this really quick. Okay, so I said that this associative array, this map is immutable, right? So let's try to do students. 404 is students type does not take parameters. This is how you create the associations, right? Students. So I guess that's the error. It's not really clear. Now let's try this other example, which uses a different associative array instead of map. Okay, so now I can add myself here, students. And I don't get the error on it. Okay? So you have to just make sure you use the right map. If you want to make changes, you have to use this beautiful map. And Scala maps implements this associative array using hash table. If you remember from CS2, that does not preserve the order of the keys or order of insertion. It really depends on how the implementation and also depends on the keys, right? But if you want to preserve the order, there is sorted map, which will use a tree to maintain the order of the keys if this is important for you. All right. All right, that's what I had planned for today. See you guys next week. Have a great week. Have fun.
What time does it don't get out of yourself. Oh, you mean
That's kind of late.
Keep that out of my head now.
I don't like the.
I know, maybe.
You're sitting where I don't want to sit. No.
Language,
I don't know, I didn't want to interrupt her flow. I'm gonna like fuck it up enough.
No, except you're.
See, that's nice. That sounds great. You know how getters and setters are the dumbest things?
Yeah, dude, that's
No, so they're automatic. So C# you can just say, if you just run it up and set, just angle parameters and after the name property get set, if you just want one of the others. If you want some logic, you can define the logic and say get.
Do you wanna go though?
and then operating value, if value greater than 0.
Hey guys, have a good weekend.
It's like, it just auto boilerplate.
That was my.
There's a built-in operator called link,
Was it?
which LIQ, which is
Theory was your
it's a bit janky because it's written in like SQL, so you know